Okay, I think first couple of slides, I really wanted to go through it real quickly, just to, because I saw a couple of assignments from assignment 3, which I didn't get a chance to review before the last lecture. And I'm going to just point out some of the mistakes, not really mistakes. I think everyone knows how to solve these problems by now. In principle, it's just, some of the mistakes are related to not knowing how to mostly quickly solve the problems or quickly check units and stuff like that. So I'll just try to go through it quickly. So the first one is the simple current mirrors. I think the first problem was related to finding out, first part of the problem was just finding out the ratio of the currents, right? So you were given a certain input, I think it was a 80 microamps here, and you were asked to find out what the output is. And I think the W1, L1 was given to be, might have the, so 100 by, I think this was 1.6, and this was 25 micron by 1.6, something like that. So whenever you have a simple current mirror like that, and the only thing which is changing is the size of these transistors, Q1, Q2, then the ratio is just this, right? So it's whatever W2 by L2, whatever this size is in correspondence with this Q1, the I out is just a scale factor of that. And here we always assume the equation where the lambda is not a factor. So in other words, the output impedance is not a factor. Because when we are calculating current, the error because of omitting lambda is very small, so we usually don't make the equations very complicated. Okay, so that's really all you need to know. If everything, because VGS is same, so I'll show in the next equation here. So like as I said, I've been making the mistake not having this 2 here. So it's mu n Cox over 2. And I think I've been writing all over mu n Cox, which is really the linear equation. So here you can see the input current is really the drain to source current IDS1, which is W1 L1 mu n Cox over 2, VGS1 minus VTN square. And the output is W2 over L2 mu n Cox over 2 VGS2 minus VTN square. Now, it so happens that these two quantities are the same. The reason they're same is mu n Cox is obviously same. These two are same because it's the same technology. Now, VGS1 is also equal to VGS2, right? And the reason for that is you can see here, both the gates are connected to the same terminal here. Both the source are connected to ground. So VGS1, whatever you have, VGS1 has to be equal to VGS2, right? So that's same too. So if they are the same, then if you take the ratio of I out over I in, then these two terms will cancel, these two terms will cancel, then all you'll be left is the two sizes, that's all. So just remember that whenever you have a simple mirror, I think some people have calculated the V effective first, and then from that V effective, they've substituted an ID2 and then found out I out, which is fine. And some of you made mistakes by doing that. That is not wrong. This is just a quick way because you know a priori that all these factors are same. So I out is just simply the size. So if the size is the same, then I out is same. If the size is 2 times larger, Q2 is 2 times larger, then the current will be 2 times larger. If 2 times smaller, current will be 2 times smaller, and so on, right? So in that first problem, I think, like as I said, it was 100 by 1.6, 25 by 1.6. So the scale factor or the size difference is of Q2 is 1/4 of Q1, so which means that the current is going to be 1/4 of in the input current. So 1/4 of 80 microamp is 20 microamps, right? So that's one thing I just wanted to quickly point out. The other thing I wanted to point out is avoiding mistakes in units. So what I see people do is that when they write equation for GM or RDS, you get basically orders of magnitude errors. So I'll So for example, when you're writing R out as 1 over lambda ID, what I would suggest is, you can choose whichever way is convenient to you, but choose one way. This is what I like. I always like to write the units, right? So once you write the units, for example, here 1 over lambda ID is L over lambda L, and this is something you get from that table 1.5. That's a technology parameter, and this is ID, right? So length is usually in micrometer, right? And this is also noted as micrometer over volt. So these micrometer will cancel, and then what you get is 1.6 over 0.12, and this this is 10 to the power minus 6. When it goes above, obviously it's 10 to the power 6 a volt per ampere, and that this unit is ohms now, right? So once you have it in ohms, then all you have to do is just calculate this and you'll get the answer. So that way you're not making a mistake. Because I think some people miss this microamp and they just get like 660 ohms or 0.66 ohms. And that's another thing you have to get used to it. So like for example, in our route, when you have 20 microamps and like roughly a 1 micron length, pretty much all technologies, you will have your resistance in kilo ohms, right? If you are having it in 10 ohms or 12 ohms or 0.6 ohms, there's a big chance that you made a mistake, unless the current is huge, like you're pumping in 1 ampere or something like that, which we'll never do in our the kind of circuits we're involved in. Same thing with when you're, let's say, finding, for example, effective voltage of a transistor, write all the units, right? So if you write all the units, then you can, like, for example, here the microamps will cancel, this volt square will go on top, this micrometer will cancel. So all you have is, volt square root over just volt, and then you just multiply these integer numbers. You don't have to deal with 10 to the power minus 6s and so on. So it's just an easier way to calculate. Like as I said, you can use, if you're comfortable with using the full number, like 1e minus 6 ampere, everything in metric units, that's fine. But just have a method, like have a consistent method where you will not make these kind of mistakes. And same thing here as well. Like for example, some of you have made a mistake where this is not microamps anymore. So you actually get this as 0.16 microvolt or something like that. Now, typically, again, if a transistor is in active region and you have sufficient amount of current going, when I mean sufficient, like tens of microamps, then it'll be tens or hundreds of millivolts. Okay, it'll never be microvolts. So if you're getting microvolts, then you're making some unit mistakes somewhere. All right. So the other thing I wanted to point out is the mismatch effect. I think some of you got confused. So mismatch is trying to find out the mismatch between the nominal and what would be the current if there was a mismatch in one of the parameters. So what it means is that if these two transistors were perfectly the same, right? So the VTs were same, the Ls were same, the beta, which is mu n, the mobility was same and everything, then if you had 100 microamp here, like we did in the previous example, you'd get 20 microamp because the size was 4 times less, right? Now, when you have a mismatch, for example, now let's say the difference between threshold voltage, that is VT1 minus VTN1 minus VTN2 is 5 millivolts. Doesn't matter which is higher, which is lower. I mean, obviously, in one case you'll get a current higher and current lower, but the difference is 5 millivolts. So what the problem, or I wanted you to find out, is because of that difference, how much does this I out differ by? I think a lot of you have subtracted from 100 microamps this number and found out the difference, but that's not what the delta is. Delta is like, if there was no mismatch, then you'd get 20 microamps. If there was a mismatch, then what is it different from 20 microamps? So in this case, for example, if you didn't have a mismatch, then the effective voltage is 167 millivolt, for example, right? Now, if you have a mismatch, then you write the same equation, right? So this is your new I out right now with a mismatch. Your mu n Cox remains the same, W2 over L2 remains the same, but this was your original v effective, VGS minus V2. You add or subtract depending on if you have your VT lower or higher. In this case, I have imagined the VT to be lower. So this is VT N2 minus 5 millivolts. So you just add that. And if you do that, then you will get the resultant current. You'll get the resultant current. Like for example, in this one I've already calculated. Hopefully I haven't made a mistake. So if you substitute your previously calculated V effective into this and add another 5 millivolt, calculate the new current, this should be your new current, right? Which is 1.26 microamps more than what you would have had if there was no mismatch. So basically delta I out over here, this delta I out is I out minus I out dash, right? So this is what I call the nominal current. Nominal current means everything is perfectly everything has their nominal values. VT has their nominal values, W over L has their nominal values, beta has their nominal values. And if something gets mismatched, then the resultant current is off by how much? So in this case, 1.26 microamps. And I think I've solved the other mismatches like length mismatch and mu n mismatch. So you can just go back and look at the solution, or and like as I said, I've made a mistake, I think, with those mu and Cox over 2. So everything would be a factor of 2 off, I guess, unless they're a ratio where they get cancelled. Okay. So we'll move on to the topics which was given for this assignment 4. So the first one I'm going to cover is the source-degenerated current mirror. So the source-degenerated current mirror is, as you can see in this picture, in a simple current mirror, you had the two transistors connected um, uh, from just like a simple current mirror. One second. So in the source-degenerated one right now, you basically get these two resistors here, RS connected to the source side of it. And we'll see why we do this. Now, the reason we'll see as we derive it is that we want to actually enhance this output impedance. We want to increase the output impedance. Remember, this is a current source, right? So if you remember the Thevenin equivalent of a current source, you actually have this RS in parallel. In a current source, you want this to be always high, ideally you want this to be infinity, right? So you want to raise this output impedance as much as possible. So this is one way of doing it, but I'll actually show you why it's not a good way of doing it, and then we'll go to the Cascode. But we'll actually use this to do low noise current mirrors, and that's something we'll do while we're doing our projects. I probably won't cover it in the lectures. Okay, now before I show the small signal output impedance, why the output impedance is enhanced, I'll just quickly go through the large signal model. Now, just to show you that if these two transistors are exactly the same, so if Q1 is exactly the same and RS are the same, then this current which is flowing out should be equal to IN. And kind of intuitive, because you can make out that, okay, if this ISRS is the same, this ISRS has to be same. That's the only way this VGS will be same. Now, I'm just going to quickly show you graphically why that's the case. So let's say, and let's say this is, I'm going to call this node VS, let's say. So let's say this is VS, and like in this problem, the gate voltage is V1, right? So let's say this is Vs and this is current, and for now I'm going to just say I out. So what I'm going to do is first graph the plot, the current flowing through the resistor. So draw it in another color, let's say in this red. So let's call this IR flowing through this resistor. So as this voltage Vs with respect to ground is increased from 0 to, let's say, V1. So let's say this is V1. And as I'm increasing this voltage, what is the current? Well, the current is going to be just linearly increasing, right? And this slope is, so that's your IR, right? Okay, now what about the current going through the transistor? So let me just plot this in green. So let's call this IDS2, the current flowing through the transistor, IDS2. Now as Vs, let's say Vs is at ground, that's the maximum voltage, and the current is going to be some maximum current around here. And as Vs gets close to V1, that means the gate to source voltage is actually turning to 0. So as we get closer, it actually gets to 0, and it will turn off. So this V1 minus Vs needs to be at least Vt before the current in this starts going up. So if I draw this is kind of the reverse plot of what we do VGS versus IDS, right? Because we are subtracting a voltage. So till Vtn, it will remain 0, and then it will start increasing, right? And so that's your IDS2, which is, our famous equation, mu n Cox over 2 W over L, and this is V1 minus Vs minus Vt square, right? So if I write that equation, this is the graph I'll get. Now, this is the same branch, which means that the only solution for these two are where they meet here, right here, right? So this is where they meet, and basically what I'm saying is that this needs to be equal to IN. This is the only solution. And you kind of intuitively see this. So for example, if I just split this voltage here is IN times RS, right? Because this slope is R, and if this is IN, then this voltage is IN, which means that this is VGS1. So basically what it means is that if the VGS2 is, let's say, greater than VGS1, then the current is going to be lower. But if that current is going to be lower, then the resistor current is going to be higher. So obviously they won't match. Now if VGS2 is higher, then the current through the drain is going to go up, but that can't be true because the resistor current has to decrease. So the only way they will meet over here is when IN is equal to I2, right? So that's kind of a graphical way to see why the currents will be equal. Now you can write the equation, complete equation also, and I'll just quickly just show you how to, in case you wanted to write it that way. So this V1, the voltage V1 is nothing but I in times RS plus VGS1, right? That is basically this voltage here plus VGS1. Now the current going through Q2, which is same as I out, right? So I out is nothing but IDS2 is nothing but mu n Cox over 2 W2 over L2, which is same, let's say, in both the cases. Then you're going to get V1 minus Vs square, right? Now, if you substitute this V1 over here, and Vs is nothing but I out times, this is I out times Rs, you'll see that the only thing which solves this equation is when I out is equal to I in. Okay. So I won't go through the whole equation, but it'll be pretty easy to see if you just expand the equation. Okay. All right. So that's just a DC large signal DC analysis to show that both the currents are the same. So the question is, why do we do this instead of just doing it as we did in the simple current mirror, because we were getting the same current too there. So I think that involves the output impedance. So I've just redrawn from the text material itself, and it's a standard method of finding out output impedance. So this is your drain node basically here. So this is your drain node. So this whole thing is your transistor, right? Which is substituted over here. So the way you find the output impedance is you apply a small signal voltage source. In this case, for example, it's Vx, and you find out how much current is flowing through it. So then that output impedance is Vx applied voltage over the current which is being drawn through it, right? So if I use KCL and write the first equation here, so Ix is equal to GM2 times VGS, but VGS is nothing but minus VS. So let's call this node VS, the source node, because the gate node is grounded, because it's just a constant voltage. So small signal wise, the gate node will be grounded. So all it is just minus the source voltage node, minus VS, plus the current flowing through the output impedance of that transistor, which is Vx minus VS, sorry, minus Vs times over RDS, or I can just write as GDS2. And GDS2 is nothing but reciprocal of your impedance, 1 over RDS2. Sometimes it's easier to write it that way. So that's your first equation, right? And then the second equation is because I want to eliminate this node Vs, and that's an easy one because whatever current is flowing through this, which is Ix in this node, has to all come out here, right? Because this current is 0, so that means this current has to be Ix, which means that Vs is nothing but Ix times Rs. That's your second equation. So if you substitute this Vs into over here, and rewrite the first equation, you're going to get Ix equals to minus Vs times GM2 plus GDS2 plus Vx times GDS2. And this Vs, you substitute Ix times Rs, and so that will, and then you reorg it, so then it'll be Ix times 1 plus GM2 plus GDS2 times Rs is equal to Vx times GDS2, right? So in other words, R out, which is equal to Vx over Ix, is, so this one, if I move it down, that becomes RDS2 times 1 plus GM2 plus GDS2, but typically always GM2 is 5 times or larger than GDS, so I can approximate this to just GM2 times RS. So that's your expression for your output impedance. So you can see that the output impedance for a simple current mirror, it used to be just RDS2, right? Now it's RDS2 plus this gain term, which I call the self-gain term. So this is that extra boost which gives you that. Now let's look at this problem here to see how much boost we get, and I'll show you what the just full slide it. Okay, so the first part of the problem was, so this is a source degenerated current mirror, and in the problem it was given that the input is 0.5 milliamps, which is basically 500 microamps here, and the sizes are the same. It's 20 micron by 0.2 micron. By the way, whenever I write just micron, it means micrometer. It's just a quicker way of writing the length. So whenever I write micrometer, it means micron. I mean, whenever I write micron, it basically means micrometer. So the sizes are the same. And basically it's asking if RS is equal to 200 ohms, what's the output impedance? So the expression for the output impedance from the previous one was RDS 2 times 1 plus GM2 times RS, right? So basically the two operating points we need to calculate is RDS2 and GM2. So RDS2 is 1 over lambda ID, which is in this case is I out. And since I out, all the sizes are the same, RS is the same like we showed in the first slide. So this is 0.5 milliamps as well, right? Approximately. So if you substitute all that, I'm just going to write the final value. I think I've calculated this to be 5 kilo ohms, and the GM, which is 2ID times mu n Cox W over L square root of that. Again, you know ID, which is 0.5 milliamps. This you get from the table. W over L is 20 by 0.2, which is 200. You put all that value, and this is 5.196 millisiemens. By the way, millisiemens is nothing but 10 to the power minus 6 amp per volt, right? If it is volt per amp, it's ohms. If it is amp per volt, it's Siemens. So whenever I write that, just remember that. Okay, so now I can write the R out, output impedance, and that output impedance is nothing but it's RDS2, which is 5 kilo ohms times 1 plus GM times, well, let's call it GM2 times RS, and this is 5K times 1 plus 5K times, I mean 0.2 kilo ohms. The 200 ohms is 0.2 kilo ohms times 5 milliohms is roughly just 1.03 or something like that. So this is roughly equal to 10 kilo ohms, right? All right, so if you had a simple mirror with the same sizes, you would have got just RDS, right? So R out would have been just 5K. This is for simple current mirror. Now, because you added that RS, you get 10 kilo ohms now. You get twice, okay? Now, there is a price to pay for it, and that's actually the voltage headroom. So what is the voltage headroom, which I call it as the voltage compliance? This was not part of the problem, but this is actually important reason why we don't most of the times use this, but use a Cascode, which I'm going to show later on. So, and the output voltage compliance is, so if you had a simple current mirror, you know, I've shown this before where I want to find out V out versus I out, and you know, it is only a current mirror after a voltage V effective, right? If it was a simple current mirror. So if you had this as your simple current mirror, so that's your I in, and this is your I out. So this voltage V, let's say V out, needs to be minimum equals to greater than equals to V effective, which is VGS minus VT of this device, right? So what is it for the RS? Now RS, you can see that this voltage is I out times RS, and from here to here, that needs to be at least V effective too, right? So in other words, V out minimum needs to be at least I out times RS plus V effective 2. So you have this extra headroom which is added. In other words, it's going to eat up your headroom from your circuit. So before you, let's say V effective, let's assume V effective is in the previous problem, let's say we calculated 167 millivolts, right? So 0.167 volts, let's say. So for a simple current mirror, as soon as your output voltage was higher than this, you wear a current mirror, and anything higher than that, you would get the same current. Well, it'll change slightly with your output impedance, but pretty much the same. Now with this new one, let's calculate with that 0.5 milliamp, and so for example, RS is 0.2 kilo ohms, which is 200 ohms, and I out is 0.5 milliamps. So I out times RS is equal to 5 times 2, that's 0.1 volts. 0.1 volts, right? So the new V out minimum I need has to be equal to 0.1 volts plus 0.16 volts, 7 volts, which is 0.267. It's just an example. So you need more voltage at the output for it to be compliant, which actually eats up your headroom from the rest of the circuit. Like for example, you're using this current mirror for common source amplifier. So the amplifier we're using, we actually want the output voltage, right? Let's say it was an audio amplifier, you want the output to be a sine wave or whatever you are inputting it from. Now, if your current mirror needs at least 267 millivolts for it to be active, that means the output signal cannot swing below that. If it swings, then it'll crush the current mirror and then it won't be a current mirror anymore. So that's the problem with this. And the other problem is, as you saw from the previous one, it only changed your output impedance by 2x. Well, it's 2x is large, but let's say I want even more, which means that I need, so let's say, for example, I need 5 times more. So which means I need to make this RS equals to, let's say, 1 kilo ohms, right? So I'll get a higher output impedance, but the problem is the drop across that resistance now, so I times I out times RS is 1 kilo ohm times 0.5 milliamps, which is equal to 0.5 volts. So now suddenly your output V out minimum needs to be almost close to 0.67 volts. Or sorry, 0.6, roughly 0.67 volts. So that's the problem. And this is the same problem as what we saw using resistor as a load for our common source amplifier, where the DC bias cannot be separated from the small signal output impedance, right? So I want to improve only the output impedance, but not do anything with the DC impedance. But here they're coupled, and so I cannot really increase my RS to a large value, and that's the problem. So the way we get around this problem is cascode current mirrors. So what we do is, instead of actually using a physical resistor here, we actually use another current mirror. So you can see this bottom part is actually another current mirror here. So it's actually two current mirrors were stacked on top of each other. So this is nothing but, if you see the previous example, degenerated current source, you can approximate this as that equivalent RS, right? So this is your equivalent RS. So if that's the case, I can straightforward write the output impedance. The output impedance is nothing but, in this case, it will be RDS4 times 1 plus GM4 times RDS2. And in cases like this one, where actually you have output impedance of a transistor, typically this term, GM, is much, much greater than 1. So you can even further write this as RDS4 times GM4 times GM4 times RDS2. VD2, right? So you're basically gaining up the output impedance by this GM4 times RDS2, which can be, we have seen in common source amplifier, for example, could be 10 to 100x depending on how you bias it. So let's say you had RDS2, which we computed before 5K. If this term is 10K, then you get 50K, from 5K to 50K um, improvement of the R out, right? So now the question here is what happens to the output impedance, the voltage compliance, right? So now what is, so let's call this voltage V out. What is now V out main such that both Q4, such that both Q4 and Q2 are active. So let's say this node voltage is, we call this VD2. It's a drain voltage of 2. So for both of these to be inactive, for the Q to be inactive, I need, well, I bias it such a way, let's say the VD2 is actually makes Q2 active. Now the question is, how do I make Q2, Q4 active? Let's assume Q2 is active because VD2 is enough for it to active, and it actually is, and I'll show you why. So in order to keep Q4 active, that means, and you know, VDS4 is nothing but V out minus VD2, right? And you want this to be at least greater than equal to V effective 4, which is basically VGS minus VT. Now this node voltage VD2 is nothing but, if I write the KVL around this loop here, is actually VGS1 plus VGS3, right? So it is, so this voltage here from this node to here is VGS1, and this node from here to here is VGS3. Then you subtract this node voltage VGS4. That's your VD2, right? That's VGS4. That's your VD2. So if I write the whole thing now, V out minimum needs to be, like as we said, VD2 plus V effective, and this is VD2. Now, if everything is size same, okay, let's assume that these are not scaled current mirrors, they're all the same, then all these quantities are same. VGS4 is equal to VGS3 equals to VGS1 equals to VGS2 and so on, right? Because they're all size the same. The output current mirrors exactly the input current. V effectives of each one of them is same. Let's say there is no mismatch. So in other words, these two will cancel. And let's say this is VGS1 equals to some VGS voltage. So this is VGS plus, and all the V effectives are same. So I'm just going to write it as just V effective, right? So I can write this as VGS is nothing but VT plus a V effective. So I can write this as VTN plus 2V effective. So this is the minimum voltage you need across this cascode current mirror. I'll show you in the next problem how to improve that situation. But this cascode mirror will require at least this voltage. So in the simple current mirror, all we wanted was V out minimum to be just V effective, right? So let's say, for example, we calculated this to be some 0.1 volts. All we need is 0.1 volts. In this case, like for example, if VT is 0.45, you need 0.45 plus 0.2 volts, which is 0.55, which is a large voltage. So it takes a lot of headroom doing this. So a lot of times, unless you have a lot of headroom, you'll use this because it's just simpler to bias. But a lot of times we will actually not use this structure because of this very reason. Although it gives you a higher output impedance, it takes away your voltage swing. So the one we're going to use is the problem I gave, the 3.22. And this is called a wide swing current mirror. Now the reason it's called wide swing is, I'll show you real quick here. Maybe you want to go back and look at the problem again, just to, because we'll be using this current mirror a lot. So, you know, make sure you get familiar to this. I wish this was an NMOS current mirror because it's a PMOS. and it's an NMOS, so it just gets confusing at times. Okay, so since this is a PMOS and this is, I want to reference everything to ground here. So let's call this node here, let's say V1, let's call this V2, and this node V3. Okay, now V1, so what I want to find, so in order to find out what's the V out max, now this is a PMOS mirror, so I want to find out V out max, right? Because the reason it's V out max with respect to ground is because as I go higher and higher, as I get close to 1.8 volts, then this whole thing will be dead. It won't be inactive. So I have to start pulling this voltage down. And so what is the maximum voltage I can have? For example, if I have 1.8 volts here, because the supply is 1.8, you can see that I cannot have 1.8 volts here. If I have 1.8, then these two transistors will shut off and I won't have any current. So the question is it 1.6, 1.7, 1.5? What is the maximum voltage? And as you go lower, then this mirror is happy. It's exactly the opposite of NMOS current mirror, right? So as you go lower, it's fine. So I need to find V out max. So from this equation, from this circuit, you can see V out max is nothing but V3, this voltage V3. And it's a little bit tricky. It depends on how. Actually, one problem I really wanted to get through was that PMOS current mirror, and I forgot about it. Maybe in the next lecture I will do it just to show how to solve PMOS circuits. So V effective is actually in PMOS, everything is negative, right? So if this is with reference to ground, you want to write V plus V effective 4. The reason you write plus is because this is actually a negative quantity. Now, if you don't want to get confused, you can write everything in terms of magnitude. So for example, you can write this as V3 minus the magnitude of V effective 4, right? You can write it this way. That's fine as well. But just choose one method and just follow it always, right? So I'll just follow this method for now. So now the question is, what is V3? Now V3 is nothing but V2. V3 is nothing but V2. And here I'll won't write magnitudes of it. So the gate to source voltage is actually a negative voltage, and the source to gate voltage is actually a positive voltage. So I'll write it as V2 plus VSG4. Okay, so that's the source to gate voltage. So the source to gate voltage is a positive voltage. Gate to source voltage is a negative voltage because this is PMOS. Okay, so I might change this thing just to kind of keep it not confusing. And V2, you can see V2 here is nothing but V1 minus this voltage across this resistor, right? So V2 is equal to V1 minus, I'm just going to call it I for now. That's I in, I out. It's the same thing, times R, right? So if I substitute over here, so that's V1 minus IR plus VSG4. That's V3. And what's V1? V1 is basically nothing because V1 is this node here, right? And that's essentially 1.8 volts minus VSG1. Okay, that's V1 minus IR plus VSG4. That's your V3. You add V effective 4 onto it, and that's your V out max. Okay. Now, if this is again a matched current mirror, everything is matched, these two numbers cancel because VSG1 equals to VSG2 equals to VSG4, 3, and so on. So this will cancel. So this is 1.8 volts minus IR plus V effective 4. Okay, so you can clearly see here that in the previous problem, unfortunately it's NMOS, it might be a little confusing. You can consider this to be your ground, right? So essentially this is your V out min in case of like if it was an NMOS. And you can see, for example, this is 2 kilo ohms. So if I calculate it real quickly, IR is nothing but, so 1.8 volts minus IR is 2 times 0.15, that's 0.3 volts. So this is 0.3 volts, and V effective, I haven't calculated, but I'm just going to assume a number. So let's say this is 0.16. Actually, this will be a negative number, so this is 0.16. Yeah, so let's say this is 1.8 minus 0.46, 1.8 minus 0.46, 1.34. So that's your max voltage. But I'll definitely encourage you to do a NMOS version of that. That'll be more clear, because if you remember in the previous one, this voltage was actually 1 VGS plus V effective, which means it was almost 0.6 volts. So the trick here is actually, if you remember the previous one, this voltage was 1 VGS plus VT. But that's more voltage than I ever need, right? Because all I need is a V effective around here. So the trick here is you actually use this resistor here and drop this current such that whatever voltage you need here, so let's say this V effective was 0.16 volts. Usually you give some headroom. And so I say, okay, I'll give another 140 millivolts headroom. So I want 0.3 here. So that 0.3, I want to drop it across this resistor here. And one easy way to see is that, let's say this resistance is 0 ohms. If this resistance is 0 ohms, this gate voltage is equal to this gate voltage, which means that this voltage will be equal to 1.8 volts. That means this will get crossed, right? So whatever voltage I drop across this resistor actually appears here. And that's why it's called a wide swing current mirror, because now I don't have to live with that VT plus 2 V effective. I can actually control how much voltage I put across here. So for example, if this was, let's say V effective was only 0.1 volts, then I can say, okay, I'll just point 0.2 volt across this. So I'll put 0.2 volts here, and all I need is 0.2 volt. Let's say this was 0.1 volt, then um, this would be just zero point 0.3 volts instead of 0.7 volts, which was a lot of headroom to lose, right? So I think what I'll do is in the problem, I'll make this a NMOS. I'll just invert this and make it a NMOS, and I'll give you the solution. Definitely take a look at it, because that'll make it clear, because we had NMOS simple current mirror. I'll show this with the NMOS, and that I think will make it clear. So I'll put the numbers in the solution, and you can see clearly why it's called a wide swing current mirror, and it saves you some headroom. So when I do the problem, it's not part of the problem I gave you, but I'll just reformat this to make it an NMOS problem. That way, you don't get confused with everything being referenced to the supply 1.8 volts, but you should get used to it. Okay, so I think I'm just going to stop here. We kind of are out of time right now. I'll take any questions, and so I'll continue with this in the next lecture, where I'll cover the rest of the Cascode stage, and then I'll start the differential stage, which is probably the most important one. And like as I said in the email, make sure you attend Dr. Prakash lecture, which will be the frequency response, because I want to start with the op-amp design, because by September I really want to get started with the project. So I want to cover the op-amp compensation. That will give you a good background, and then anything we need after that we can always discuss one-to-one, or I can just take a lecture as I'm doing right now.